Welcome back. Now we are going to look at some points to discuss regarding the first law. We have seen that the first law, the final quantitative form, is Q equals W plus delta E. This includes the first law, it includes the definition of delta E, it includes the definition of the heat interaction. Let me transpose and bring delta E to one side and Q and W on the other side. If I do that, then I will get the following form. Delta E is Q minus W. Or in the differential form, we can write dE is dQ minus dW. Okay. It is important to note here that in this form, delta E is Q minus W, delta E is change in a property, whereas Q and W are both interactions. In the second form, which is a differential form, dE is an exact differential, whereas dQ and dW are both inexact differentials. This should be remembered. Because they are inexact differentials, we may sometimes cross the stems of the d or write them as d prime q or d prime w. Whether we do that or not is unimportant. More important to remember is that they are inexact differentials, or that q and w are interactions. Because q and w are interactions, remember that whenever we talk of q or whenever we talk of w, there must be two systems involved, a system A, system B, or a system and its surroundings. Then the interactions take place across a boundary. So there is no way one can talk of Q or W without associating those interactions with a boundary. Okay? And these interactions must cross those boundaries. And because these are interactions, we can consider them as energy in transit. Q and W are not contained in a system. It is always work done by a system or heat absorbed by a system. There is an illustration of this which I came across in some book. Is that consider a cloud contains water vapor, water particles. On the ground we have a lake which may contain some water. When it rains, water gets transferred from the cloud to that on the ground in the lake. So what we have is rain, which is nothing but water in transit. We don't say the lake contains so much of rain or the cloud contains so much of rain. Rain is only water in transit. In a similar way, heat and work are energy in transit. Another aspect to remember is the expansion. We should remember that the work interaction is made up of a number of modes. In the general case, we would have expansion work plus stirrer work plus electrical work plus what have you. Okay. Similarly, delta E can be expanded into change in potential energy. Again, this potential energy could be change in potential energy due to gravity, change in potential energy due to change in electric field, change in potential energy due to magnetic field, plus what have you, plus change in the kinetic energy, plus there could be other components defined by other branches of physics. So there could be our so-called primitive components. But after that, it turns out that a system can have a change of energy in spite of there being no change in any of the primitive components. That is known as the thermal energy of the system. Change in that is represented by delta U. This is the thermal energy of the system. This is special to thermodynamics, and in many of the situations, many of the simple situations that we consider, we will find that of all the components of delta E, delta U will be or will generally be the most significant component. And now coming back to the first law, if you consider Q equals W plus delta E as our format, then the expanded form will turn out to be Q equals various components of work summed together plus various components of delta E summed together plus or including the thermal component. So this is the expansion of W, this is the expansion of delta E. Now let us look at cycles. Let us consider a system, or let our system execute a cycle. That means we start with an initial state 1 and maybe execute a cycle partly quasi-static, may not be partly quasi-static, but anyway it is a cycle, so that the final state 2 is the same state as the initial state. So a cycle is executed of any kind. Now because the initial state and the final states are the same, the change in energy of the system over a cycle will be 0. And the first law now reduces to Q equals W for a cycle. If you are able to determine these two interactions by integration, we can write then the cyclic integral or integral over a cycle of dq is integral over the same cycle for dw. So these forms are known as first law for a cycle. Now before we complete this basic discussion of first law, there is one question which comes to our mind. We have always been saying and discussing adiabatic processes, and we have said that let a system go from state 1 to state 2 by some adiabatic process, quasi-static or otherwise. The question is it always possible to execute an adiabatic process from a given state 1 to another state 2? Well, we will have to study the second law before we come to an answer for this, but the answer is not necessarily. But now looking into what we are going to study a few weeks later, the second law of thermodynamics will tell us that if 1 to 2 by adiabatic means this process is not possible, then 2 to 1 by adiabatic, the other process starting from 2 as the initial condition and ending up at 1 as the initial condition is definitely possible. And hence If we want to determine W adiabatic 1 to 2, and if 1 to 2 does not seem possible, then we can always execute an adiabatic process from 2 to 1 and take the negative of that as the value for W adiabatic 1 to 2. Thank you.